Okay, sample problem 4.4. Milk of magnesia, an over-the-counter laxative, is a mixture of magnesium hydroxide, MgOH2, and water. Because magnesium hydroxide is insoluble in water, milk of magnesia is a suspension rather than a solution. Okay, so it doesn't dissolve completely, so you see little particles floating around. That's what gives it the milky type visual appearance, is that it's a suspension, meaning that little particles are floating around in it. The undissolved solid is responsible for the milky appearance of the product. When acid such as HCl is added to milk of magnesia, the suspended MgOH2 dissolves, and the result is a clear, colorless solution. Write and balance the molecular equation, then give the ionic and net ionic equations for this reaction. Okay. So let's go ahead and go through this one. We're going to do, this is an acid-base reaction. We did, in the previous example, a molecular ionic and net ionic equation set up for precipitation. But this is acid-base reaction, okay? Acids and bases. So here's how we approach it. It's pretty much the same idea. There's just a couple of differences that we'll look through. So the first step, again, is you do the molecular. Step one, do the molecular equation. Okay? The molecular equation, again, you write down the chemical formulas. Now, I'm going to write the HCl first, and then the MgOH2, but it doesn't matter which order you put it in. Then I'm going to do states of matter. So acids dissolve in water, so they're aqueous. Magnesium hydroxide, it says it's insoluble in water, so that's solid. And then we write the arrow, okay? Just like we did with the precipitation. You write the two reactants together with a plus to indicate they're different substances, then you draw the arrow. Now you predict the products. Now, here's the way it works out. Very much just like the precipitation. There's a plus and there's a minus, cation, anion. There's a plus and a minus, cation and anion. Switch partners. So the H plus is going to go with the OH minus to form water. Okay, I'm going to write down here that this is H plus OH minus. Water, is, you can think of it as H plus OH minus. Okay, and then the magnesium is the plus, that's going to go with the chloride. Going back to the periodic table, magnesium has a charge of +2, chloride has a charge of -1, so we need 2 of the chlorides to balance that charge. Then you do states of matter. Water, this reaction is occurring in water, so it's liquid, not aqueous. And then the question is, does magnesium chloride dissolve in water? If you go back to the solubility guidelines, chlorides dissolve in water unless they're with silver, mercury, or lead. Magnesium is not one of those, so this is aqueous. Okay? So there you go. Now, is it balanced? I don't think it is, because if you look, there's 1 chloride on the left and 2 on the right. So what if I put a 2 here on the left? Now I've got 2 chlorides. We've got a total of 4 hydrogens on the left, but only 2 on the right, so I'm going to put a 2 there. And now that's the balanced molecular equation. States of matter, balanced equation, correct formulas. Okay, there's a lot in that, right? That's a lot of stuff, and that's just the molecular. Now we're going to move on to the ionic. In the ionic, it's really just like we did in the precipitation reaction. The ionic equation, what you do is anything that's aqueous, you break it up into ions. Anything that's non-aqueous, you do not break up. So HCl and MgCl2 are both aqueous. Those ones get broken up into ions. There's 2 HCl's, so 2 hydrogen ions and 2 chloride ions. MgOH2 is a solid, so you don't break it up. Again, we're going to have problems with having enough space here for the ionic. So water, so I'll write on a different line. water, liquid. That's not aqueous, so we don't break it up. And then MgCl2, that is aqueous, so we break it up into ions. You may notice that sometimes I'll do the charge, the number, then the charge, so 2 plus first. Or I might do plus 2, doesn't matter, either word. And then there's 2 chlorides, 2 Cl minus. So this is a common mistake. Notice that 2 goes out in front. Okay. So there's your ionic. Okay. Finally, the net ionic. Net ionic equation, what you do is you say anything that's identical on both sides you can cancel out. Looking at this equation, the only thing that's identical is the chloride, the 2Cl minus. Everything else is different. So you can cancel the 2Cl minus and just copy down everything else that's left. So 2H plus aqueous, MgOH2 solid. Now I might actually be able to fit this in one line, right? Because we canceled out the chlorides. So it's going to be 2 waters. I'm just copying down from the ionic equation everything that I didn't cancel, plus Mg2 plus. It should still be balanced. All 3 of these equations should be balanced. In particular, if I did the molecular equation correctly, everything else should work out pretty much the same way. So let's see. In the net ionic equation, there's 4 hydrogens on the left, 4 on the right. There's 1 magnesium on both sides. There's 2 oxygens on both sides. The charges actually are the same on both sides too. Now that's an interesting aspect of balancing equations. We'll talk more about that when we get to redox equations. There's 2 positive charges on the left from the H+. There's 2 H pluses. And then the magnesium on the right has a charge of +2, so the charges are the same as well. So molecular ionic net ionic equation for acid-base reaction.